So let's take a look at some examples. We just want to determine if two sets are equal. Two spanning sets of vectors are equal. Okay? Now, we just saw that how we could do this is we could check if each vector in each spanning set is in the other spanning set. Okay? So if this vector is in here, then that means that set V is a subset of set W. Okay? If each one of these vectors in the spanning set of W is in set V, then that means that W would be also a subset of V. If V is a subset of W and W is a subset of V, then the two sets are going to be equal. Okay? All right. So let's first check if this is in W. So to do that, if vector 9, 0 is in set W, then that means that 9, 0 would have to be, we'd be able to write it as a linear combination of these vectors. Okay? So let's test it out. So 9, 0 equals some constant times negative 8, 0 plus some constant times 0, 0 plus some constant times 5, 0 plus some constant times negative 2, 0. Okay, now this one's probably simple enough that you could do it in your head without having to write all this out. But just to be very clear, we are going to write it all out. Okay, so I could present this as a system of linear equations and solve the system, but in this case, we could eyeball it. In particular, I notice that, say I take A1 here. If I take A1 and make it into negative 9/8, then negative 9/8 times the vector negative 8, 0 is going to be equal to 9, 0, right? This scalar multiplication is exactly this, which means I can make all of the other scalars here just 0. Okay? And so, hey, checks out. We were able to express vector 9, 0 as a linear combination of these other vectors. Since this one vector, therefore, then is in set W, and this is the only vector in the spanning set for set V, it must mean that vector V is a subset of set W. We have vector V is a subset of set W. That is, every vector in set V is also in set W. Every vector that can be expressed as a linear combination of this vector could also be expressed as a linear combination of these vectors. Okay? Okay, so we have the subset going one direction. Is it going the other direction? Okay. Is W also a subset of V? In order for that to happen, each one of these vectors must be a linear combination of this vector. It must be in this span. Okay, so let's check them one by one. So negative 8, 0, can we express that as some scalar times vector 9, 0? So I'm checking to see if this first vector in the span of W is a linear combination of this vector. And we could see pretty clearly that it is, right? It's going to be negative 8/9 times 9, 0. Okay? So this first vector, Check. We need to check every one of these vectors now. What about 0, 0? So 0, 0, is it equal to some scalar? I'll call it, let's use different letters actually. Let's call this B1, let's call this B2. Okay, times vector 9, 0. Well, yeah, I can use 0, right? 0 times 9, 0 is equal to 0, 0. So this one checks out too. Okay. Now you could probably eyeball the rest of them, right? I can multiply vector 5, 0 by a scalar to get 9, 0, right? I could multiply negative 2, 0 by a scalar to get 9, 0. So all the vectors work out. So what would this be? 5 ninths, 9, 0, just to show you exactly what it is. Notice I don't even need to identify the scalars. If you just can look at it and know, oh yeah, there's definitely a scalar that will make this happen, then you're good. Okay, so that means vector W is also a subset of vector V, since every vector in the spanning set of vector W is also in vector V, can be expressed as a linear combination of this vector 9, 0. Okay, so V is a subset of W. Every vector in V is also in W, but also W is a subset of V. Every vector in W is in V. Thus, V and W must be equal. They have exactly the same set of vectors. All right? Let's look at another one. What about this one? We have the span of 7, 8, negative 8, and W is the span of 0, 0, 1, negative 7, negative 8, 8. Okay, so let's first check if V is a subset of W. Okay, that means every vector in V would have to be in W, and that will be true if every vector in the spanning set is in W. Okay, so can we express vector 7, 8, negative 8 as a linear combination of the spanning set of the vectors in W? So some constant times 0, 0, 1 plus some constant times negative 7, negative 8, 8. Okay. Again, we can eyeball this. You could try solving it, setting it up as a linear system of equations and getting it in reduced row echelon form and solving it. But this one's simple enough. We could see that if we set the first coefficient to 0 and the second to negative 1, it's going to work out. Right? So it checks out. Which means this vector is in W because I could express it as a linear combination of these vectors. That's what it means to be in the span. Okay, and so V is a subset of W. Because this one vector is in W, every linear combination of this vector is also in W. Okay, let's go the other way. Is W a subset of V? So to check if W is a subset of V, we need to check if each one of these vectors in the spanning set of W can be expressed as a linear combination of this vector, if it's in the span of V. Okay? So let's start with the second vector. Negative 7, negative 8, 8. can we find some scalar to multiply by the vector 7, 8, -8 to make this equality work? Well, again, it should be pretty obvious. -1 will do the trick here, right? So that works. Okay. So this one and this one work. What about this vector here, 0, 0, 1? Can I express 0, 0, 1 as a linear combination of 7, 8, -8? Well, in order to do that, I need 0 up top in the first entry. So something times 7 needs to be 0. That would mean this has to be 0, right? So B2 has to be 0. But if B2 is 0, that means 0 times this would be 0 for the whole vector. 0, 0, 0. I want 0, 0, 1. So there is no possible choice for B2 that's going to make this work. Okay? Which means since vector 0, 0, 1 is not in set V, this vector here is not in this set, that means W is not a subset of V. Okay, is not a subset of V. Therefore, V and W are not equal sets. Okay, V is a subset of W, but there are vectors that are in W that are not in set V. So if we were kind of to draw a diagram, maybe V, these are the vectors in V. W has everything that's in V, but then more.